Hello and welcome to the 6th tutorial. Last time we ended with an apparatus that could identify a certain number in the program counter and make a specific signal per channel. Just for 6 bits, 64 channels, 64 separate signals. And this is fed into the program board. Here you see them in view. On the top it has 16 control signals, so you can manage 16 things on your computer. Some examples, and the last pins, the last 8 pins, that is the entry for the first 8 signals from the program counter. This program board will give you synchronization with the clock, so one command you give will happen before the other. But also within the clock cycle you need to have an order. For example, if you want to read something from the bus, you first have to put something on the bus. Otherwise the bus is empty. First I'm going to explain to you the program machine, and then I'm going to disclose to you how the synchronization within the clock cycle is being done. First, on the program board we have to deal with another issue. We can signal multiple devices on our board simultaneously. That means that we have to have enough power, and that because of that I put in a buffer on every of the 16 channels. I give you the schedule of the board as well in 2 slides because it's a bit complicated, and you'll find the Jabber files on the Google Drive, of course, as always. For the first time I used a double header on the NOT gates, the octal NOT gates, which are actually 9 because I had room to spare. But I think you'll notice the description that the upper layer is the in and the bottom layer is the out. After the programming sheets we come to a very special machine. That's the control electronics of the computer. Also on Ben Eater's computer design it was quite difficult, so I try to explain it brightly. First remark I need to make is that we have a clock and that we have to have a synchronization within the clock. You cannot do B out, that means get data from the bus to B register if you didn't leave data there. So you need to do A in, B out. And that's why we built in a delay. So we have a clock cycle and we have a delayed clock. I represented it by 4 NOT gates, which take time to switch, and that's the delayed clock. Here you see which control items are delayed and which are not. So CE, ALU, register out, etc. is direct, but the in register in, the ALU register in, the display, the ALU A in, ALU B in are delayed. To get a good result for synchronization, I end the signal with the clock. But because AND is not a good gate to use in my system, I have used a NAND gate and a NOT gate. I've done this for every channel except one which we don't use yet. So it would be a good idea to build a board with 8 AND gates, or if you are precise, NAND and NOT gates. I'll show you a photo of this board. I put them together on one base plate and I made a... Please notice that approximately half of the pins are connected to the delayed clock and the other half are connected to the real clock. It's important which is which. I hope you can make sense of this. If you find these pictures not clear enough, they're of course on Google Drive, always. I decided to give you one challenge, and that is the jump situation. We have a carry signal, so if the ALU is higher than 256 a signal burns, we can jump just because we say jump, or we can jump on carry, which is a signal which only jumps if carry is on. In the red square needs to be some logic gates. This is the challenge. Decide on what logic gates you would use. I'll show you at the end of this tutorial. I set the board up in a way that I put a analyzing 8 LEDs on the left side of the control panel. When the clock reaches 8, it will give the value it receives. There's one. I put in the CE, on always, because I don't want to disrupt the computer. Here I go to the second 8, wait for the clock is 8 again. There it goes. Now for the whole system, the result of the control, you'll see that it checks out every register there is. It will start with 8. On the left, on the right, all the lights go to a certain value. I think I do it again. You get an impression how powerful this control electronics is. Nice if it works. I gave you a challenge earlier in this episode. Here's the result that I came up with. An AND gate, which is a NAND gate and a NOT gate, and an OR gate, which is a NOR gate with an AND gate. If you came up with another solution, I'd be most interested, really. One final note on the control system. You've seen that I used 16 control lines for this computer. In the future I will need more, because I would like to address RAM and ROM more extensively. For more control I can go as wide as I would wish to, but I think I'll go to 32 signals. That gives me some space in the ALU and also some space for RAM and ROM. I'm not going to bit 4K RAM with transistors, if you don't mind. Well, this is this for this episode. What can you expect from me in the future? I need one more tutorial to finish off the control section, but then I'm thinking about having the last 2 tutorials about troubleshooting, because I try to show you how it works, but it doesn't work always, and troubleshooting is a good skill to have in this regard. Well, thank you for watching. Please like and subscribe. I always forget that. And see you next time.